My name is Kaushik Balasundar and my team members are AB J. Kotur and Akash S. Nabiar. We are from BMS Institute of Technology and Management, Bangalore. We present to you the Pandora's bot, an autonomous robot which will drastically help reduce the spread of the novel coronavirus by minimizing the contact of healthcare workers with potentially infected patients by hygienically delivering food and essential supplies to those in quarantine facilities and hospitals. Now more than ever, a robot can be a game changer in containing the spread of this dreadful disease. As a result, our main criteria when thinking of a solution was to use software and hardware which are both simple and easy to scale. Using open source software stacks, easily available materials, and widely accepted standard dimensions, we designed an ergonomic food and supplies delivery robot. It has a UV disinfected cabin space composed of multiple distinct compartments to hygienically store food and essentials. Particularly, we use the adaptive Monte Carlo localization package along with the MoveBase package, which is already built on top of the ROS navigation stack for executing simultaneous localization and mapping to facilitate autonomous navigation. The robot features a battery-powered mobile base which is actuated by a DC direct drive motor, and we propose to use Hall effect sensor encoders to achieve odometry. Aruco markers can also be placed wherever applicable as an additional source of visual odometry. An RGBD camera is used to perform mapping of this area to generate and store a map of the environment. During the mapping process, keyboard teleoperation can be used to control the robot remotely so as to prevent the controller from any hazardous exposure. Once the map has been generated, the robot is roughly localized in the environment at a predefined start position. Once food and essentials are loaded into the robot, it is now autonomously ready to deliver these items in these quarantine facilities. Let's take a look at the demonstration of this robot's functionality. You are currently seeing the TurtleBot robot used as a reference for our robot. Our robot is dimensionally and functionally very similar to the TurtleBot, and thus the navigation stack can be easily transferred. Once the food and essentials are loaded onto the robot at its starting point, the operator selects the room number at which the food and supplies are to be delivered using the robot's onboard graphical user interface. The occupants in the room are informed about the arrival of the robot much in advance. The room number is then directly translated into a distinct pair of global coordinates on the robot's inbuilt map. These global coordinates are then fed in as waypoints for the robot to traverse. The local planner and global planner in the ROS navigation stack work coherently with one another. The local planner ensures that unprecedented obstacles in the course are safely negotiated, and the global planner ensures that the final destination is reached amid these local maneuvers. Upon reaching this waypoint, the compartments open for the patients to take their supplies. Once done, they confirm using the robot's graphical user interface. This confirmation automatically triggers the next room for delivery as the subsequent waypoint. One or multiple rooms can be allocated to the robot at any given time, as long as it is within the map generated prior to the deployment. Once all deliveries are completed, the robot automatically returns to its starting point for disinfection and reloading. It can also autonomously be programmed to go to a charging dock so that it can autonomously charge and always be ready for deployment whenever required. Designing a modular robot which can be retrofitted with additional external functional units was a design challenge. Ensuring accurate odometry while mapping was also a challenge. This is especially true in constrained spaces. Sometimes the wheels tend to slip or collide against obstacles, thus introducing errors in odometry, and thus the map created will be inaccurate. Finally, we had technical challenges in making the robot traverse the generated path in a straight line. It would exhibit rotational maneuvers each time there was an uncertainty in odometry. Inherent properties of the TurtleBot had to be modified to resolve this issue. The current completion status is that the finalized design and rendering has been completed to be put into production. The open source software stack, which has already been rigorously tested by several users, ensures that easy scalable deployment is possible. Simulation confirms the successful working of the various software components of the modified software stack that we have used.